Okay, and I think I saw there on the back of the notes, there's probably a couple on the uses of radioisotopes that we didn't quite get to, so you might have to look them up.
Well, they were in
So this changed a little. The only real equation that you have that I gave you was this first one here that I just erased, actually. Let me rewrite it. The equation that I really want you to know is total time is equal to the half-life times the number of half-life periods. Okay? And that was really the only equation. They used to have a few more, so that's the only one you need to know. And that'll take us down here into our problems. So for the first one here, it says a 10-gram sample, iodine 13153 has a half-life of 8 days. A 10-gram sample was allowed to decay for 32. What fraction will remain? So we need to find the fraction remaining for this, and the first thing that we have to do is find the number of half-life periods. So we take our total time, and we have to divide it by the half-life of iodine. 32 over 8 gives us 4 half-life periods. Next, they tell us the original amount, so we take 10 and we break it down 4 times. Now, they specifically wanted the fraction remaining. So in this case, there's a couple different ways to do this. They want to know basically what does the decimal 0.625 equal in a fraction, and it is indeed 1 over 16. So there's a couple different ways you can figure that out. You can use your calculator, or the other way to do this, it doesn't actually matter what you start with. If you take, for example, 1 and just use the same number of half-life periods, which is 4, you can easily find the fraction. So 1 divided by 2 is a half divided by 2 is a quarter divided by 2 is 1/8, 1/8 divided by 2 is 1/16. Hannah? That would absolutely work out just as well. So, yep, Hannah, if you just take 0.625 over 10, although what does that give us? That'll give you 0.0625, which is equal to 1/16. But then what you might have to do, Hannah, so if you take your 0.625 divided by 10, you will get 0.0625. That's still a decimal. So then you might have to just literally start going, okay, is that, you know it's not a quarter because that'd be 0.25, but you might try 1 over 8. Okay, it's not that. You could then try, okay, is it, 1 over 16, and there you got it. So you might have to do guess and check if you don't have a calculator that will convert it to a fraction. Absolutely. Yes, good question. It cannot be graphing. It can be scientific, but not graphing. So fraction remaining there is actually going to be I think originally I said fraction remaining was 0.625, and it's not. It's 0.625 over the original, which is 0.0625, which is 1/16. Or again, you can just go from 1 and break it down 4 times, and that will actually give you the fraction remaining. Half-life. 100 grams of the radioactive isotope decayed to 12.5 grams after 90.7 years. What is the radioisotope? And for this, we're going to end up finding the number of half-life periods because we know the starting and ending amount. So 100 to 50, 50 to 25, and then 25 to 12.5. So we have 3 half-life periods. Now, if we take the total time and divide it by 3 half-life periods, we can solve for the half-life. And you should have gotten 30.2 years. Who got that one? Nice job. Madison, you did not?
No, I did. I multiplied them.
Okay. Now, Madison, if you look at your equation, it says this. Total time is equal to the half-life times number of periods. So if you're trying to find t to the 1/2, you divide both sides by the number of periods. So you take your total time divided by the number of periods. That's why it's dividing, not multiplying.
Wait, what does t to the 1/2 mean?
That equals the half-life. That's the one half-life. Yep, that's that. So in this case, the half-life is 30.2 years. So every 30.2 years, you'll take your starting amount and cut it in half. Initial amount. A radioisotope has a half-life of 10 days. 1 gram remains after 40 days. What was the initial amount? This one we have to kind of work backwards. The first step that we need to do is find the number of half-life periods, and that we do by taking our total time and dividing it by our half-life. So 40 over 10, and we get 4 half-life periods. Now, once we know that, take what was remaining, which is 1 gram, and build it up 4 times. So I'm going to do this down here at the bottom. 1, multiply it by 2. So we're multiplying now, not dividing. 2 times double it is 4. 4 times 2 is 8. 8 times 2 is 16. And your starting amount would be 16.
I wouldn't pay ones on that one.
Wait.
I got 5.
Wait, so you went 1 by 1 is 1, 1 by 1 is 1?
You had 1 and then 2 and 3.
Oh, I got you. So you added 1 is what you did. You added 1 instead of multiplying by 2. Yes. That's better than going 1 times 1 times 1 times 1. Oh, it's 1. Anything else on that one? Who got that one? So, Krista, do you know what you did? Did you get the number of half-life periods? Yeah. Okay, that's good. Okay, so you put an answer of 4. Yeah. Yep. So what you did is you found the number of periods, but then you have to do the arrows to get back to the starting amount. And see how it said you ended with 1 gram? So that's why you start with 1, and then you double that 4 times. So 1 times 2. So each arrow, just for everyone's sake here, guys, as a review, remember the arrows are what is represented by the half-life periods. Okay, so that's why you double it up the 4 times. Okay, on the back. Fraction remaining. In this case, I thought it was easiest to, first of all, take our total time, divide it by our half-life to find the number of half-life periods of 4. And then if it gives me a fraction remaining problem, I like to usually start with 1 and just keep it in a fraction the whole way down. So I'm going to break 1 down 4 times using a fraction. 1 to 1/2, 1/2 to 1/4, 1/4 to 1/8, 1/8 to 1/16. And so you have, again, 1/16 remaining. Now, you can do it, Hannah, how you said earlier, because it's really the same problem. You could pick anything, even like 100. Break it down 4 times, you'll get 6.25. Then take 6.25 over 100, you'll get the decimal 0.0625. Then fish through your calculator, doing trial, guess, and test, and that will be 1/16. Good job. Okay, how many people did not know how to do number 2? Faith came in, in the beginning here, and she's like, I don't know how to do this one, so I walked her through it, and I think you will find that you actually do. The question is where do you look? So Faith, it says write the equation for the beta decay of cobalt-60 used in cancer. What do I start with? Cobalt-60. So Faith, is the 60 the mass or the atomic number? That is indeed the mass. What I need to do now is look at the periodic table, find cobalt, and get the atomic number. And it is what? 27. So that goes right there. Now, at this point, it's giving you a little information. It says it undergoes what type of decay, Rowan? Beta. So I'm going to come over to this side, and I'm going to write out a beta particle. And I do that, if I forget where that beta particle is found or the notation, I can immediately look at table O. Obviously, table O gives me my beta particles right here. So I write the beta particle next. You got it. So then the next thing you do is exactly, I bet if I would have written this, everyone would have figured it out. Yeah. So here, Hannah, let's go to what you just said. What can you add to -1 to get to 27? Good. That is the atomic number. Go to your reference table to find the symbol. What is the symbol for with the atomic number 28? Nickel. And what can you add to 0 to get to 60? That's an easy one. So your answer should be cobalt 6027 produces a beta particle and a nickel 6028 atom.
Oh, so it's like the same as what we learned.
It's exactly the same. It's just knowing where to look. You got it. It's exactly the same. Now the next one, I'd like you to try on your own, knowing what we just did, and then I'll show you the answer really quick. This says, write the equation for the alpha decay of americium 241. Yes, I will. I was actually going to look here because I don't think it's listed on your table. Now, you're right, it is AM. Let's just say, though, oh, this is a doubly bad one. They won't actually give you this. And the reason why is Table S does give you most of the names, and I wanted to review this table for the elements, but unfortunately, it stops before americium. So americium is AM. But now that you know that, you should be able to get it. So look up on your reference table, find your AM. Which is atomic number of 95 if you're looking. And let's see if you can get this. If you think you got it, I'm going to just ask you to write it out for me. Anyone think they got it? Okay, go ahead. Give us our first one here. AM what? Good job. Okay, it undergoes alpha decay. What do I write for alpha decay? Perfect. He42. And did you get your last unknown? You got it. But I have, you said 93? Perfect. Yep. 237 NP 93 is 100% correct. It does not matter if you put the helium first or the NP first, as long as they're both on the right-hand side of the equation.
What if I put A?
Instead of AM.
No, like instead of HE. Like
Not good.
But it says or.
Wait a minute.
Like it says or.
So you used your reference table to find the alternative symbol, you're saying.
Yeah, like
That's absolutely fine, but I didn't think it was expressed as A.
it says or to HE or to A.
That's not an A.
What is it?
That's alpha.
What?
Okay.
Yeah, but-
Oh, you meant Greek letter A.
Like I just drew an A.
That's right. You can do that,
It says the symbol is
but that's fine. But you can't do this.
A. Well, then why is an A in here?
It's not. It's
Yeah.
alpha.
Are you blind?
That is an A. Yeah.
This
I'm
is not an
but
A.
It says symbol. The symbol column.
That's an A.
No, it's not. It's not. That is not this. That is this.
And why would they write that?
Because it is the alpha, beta. This is the first letter of the Greek alphabet. This is the second letter of the Greek alphabet.
Then why-
This is the Greek alphabet. These are not. This is the Greek alphabet, not our ABC.
But it's drawn like
It looks like it, but it's just it's actually
So
got the
if you
tails.
put that on the regions, it would be wrong.
Mm-hmm. If you did, if you
Then they
did,
should not
if
put
you
that.
did that, that's not an alpha particle. That's what I was. I know what you're saying. That's an A, but it actually isn't. It's, you can do this though. That's absolutely correct. Okay, number 4. Going back, very similar to the ones that we've done before. It says, what is the radioisotope's half-life? Well, you've got to take your total time, 21 years, and divide it by the number of half-life periods, which we already counted up here to be 4, because we broke 100 down. And you get 5.25. Who got that? Oh, yeah. Everyone got it. Madison, you got it, right? Yeah. So, well, the answer is 5.25.
Well, I meant number 4.
Okay. Hey, that was 100%. Good job. Number 5, you should have gotten 80 grams. 6, also 80 grams. Questions on those? On how to get them? Good job. And this is the one that we didn't quite get all the way through. We did the first 2 and the third and the last one. Carbon 14 is used to date living things. Iodine 131 is typically used as a medical tracer, but also to treat thyroid cancers or thyroid disorders.
These are all in our vocabulary.
Yep, that's right. So you did know them. Thank you. Tenectium 99 is used in brain cancer treatment. Cobalt 60 used in to treat cancerous tumors. And uranium 238 dating rock or non-living things.
For Tenectium 99, I put bone scans.
I think I also had that down for bone scans.
Oh, that was what we told me.
That was in the what?
The vocabulary.
Yeah. So go with bone scans as well. Yep. Good job.
Are we going to have to know these on a test?
You do have to know those. They will ask you. That's why I actually include them in the definitions. That's pretty specific, but they want you to know some of those uses of radioisotopes. You don't have to know more than that, but you need to know those. Usually they're pretty easy. Carbon 14, most people are going to know, okay, living things, dating. Uranium 238, most people know from earth science, used to date non-living things. The middle 3 are the ones that are obviously, you wouldn't know that probably without having taken or looked it up. But, yep, very good. Okay. Well, let's jump on here a little bit more. We'll finish up this part of, I know that you really already know this because you just proved it to me, but I'll give it to you just so you have it in your notes, and then we'll get on here to talking a little bit more about radioisotopes.
Do you have that,
Great reminder for me because I forgot to print it for you. I will. Yep. Thank you. So in our notes here, we are at number 4, which is medical procedures. And again, I know you know these because we just went over them. Medical tracers are radioisotopes that are quickly eliminated from the body. And what does that mean about their half-life? Yeah, very good. You need something there that has a short half-life. We don't want it to be a long half-life, which keeps you radioactive for a long period of time. It needs to be a short half-life. And we also need it to emit something that's fairly low on the hazard scale. So what type of radiation is the least hazardous? Alpha. So it'd be good if this was some type of an alpha particle emitter. We don't want it to be what? Gamma. That's right. We don't want gamma. Iodine 131, thyroid disorders. Really common for the use of thyroid. Thyroid problems are pretty prevalent. Name a couple of thyroid issues. Yep. Hyperactive. Hypoactive. So there's hyper and hypo. You can have an overproductive thyroid or an underproductive thyroid. A lot of thyroid issues is related to dieting, but also weight gain or weight loss. Some people that struggle with them can have, like they can gain weight really easily or they don't gain weight easily. So sometimes that's an issue more with your thyroid than even your diet. But yeah, pretty common disorder. B, destroying tumors. Cobalt 60 emits large amounts of gamma radiation. And so that is something that is oftentimes used in radiation therapy. Gamma radiation, you might not have known this one, it's used to what's called radiate food in order to kill bacteria growing on it. And this is used to basically increase the shelf life of fruits and vegetables. Now, that is a really good question. I'm glad you asked. The question is it safe? Most people would say it is. But there are some people that don't want to eat radiated food. So if you go to the supermarket, a lot of the foods that you see are radiated. And that's why they have a little bit longer, basically, shelf life than if you pick a fresh fruit or vegetable. And those tend to start to spoil or rot pretty quick. You can't, if you for example take a fresh strawberry, and in particular talking about your soft fruits, if you take a fresh strawberry, and you just leave it on your table, how long is it good for? What's that? That's what I'm thinking. I'm thinking you can get one day, if it's a full 24 hours, maybe a day and a half before you're like, all right, that's so mushy, I don't even want to eat it. Well, store-bought strawberries, you might get 3 days, 4 days before they're really bad, and that's due to the fact that almost all of them are radiated. It does a really good job at killing bacteria. Some people wonder, okay, is it then changing, some of the chemical makeup of the food, making it dangerous? Most people don't have a major issue with it, but some people would say there could be some issues. TC99, Tenectium-99, is readily absorbed by cancerous tumors. Once tumors have absorbed the radioisotope, the tumor can be detected by a scan. So that's also kind of like a tracer. It's absorbed into tumors, and then it's basically showing up on some type of scanning device, so it kind of can pinpoint where the tumor is in the body, which is the first step in knowing how to target it or remove it. Radiation risks. I want you to know this term called mutagenic. What does that mean? Yeah, they can basically agents of mutation, or they can cause mutations. And basically a mutation is simply a change in what? Change in the genetic material, change in the DNA. And the reason that's not good is because when you change your DNA, it can lead to autoimmune diseases. Okay, so I always harp on people about, tanning, because of the fact you're exposing yourself to UV rays. That visible light is a low enough frequency that it doesn't harm you. But right up from visible, you get into UV, and there's UV A, B, and C. Well, that UV A and UV B is the next one up from that is X-ray. So people sometimes don't realize how much radiation you're getting. So yeah, I'm not a big proponent of tanning because of the fact I feel like it exposes people to UV that they don't really need. But
My doctor told me to go tanning.
really?
Yeah, because I have this skin disease and
Now, are you vitamin D deficient?
I don't think so.
Okay, because vitamin D comes
But,
from sunlight, so I was wondering if that might be why.
I don't know what it is called. It's I don't know, but I have little bumps all over my skin. And
Okay.
They told me to tan because
Wow.
it makes them go away. But
Well,
I don't because
Maybe,
I've
and
been
again, maybe
not
there's
tan.
cases where it is good.
Trampoline incident last year. Yeah, that's.
Where you burned and got fried, or
But yeah, I fell asleep on trampoline.
Oh.
I literally was
a lobster.
yeah. Zoe smacked me.
She did not.
Yeah, it turned purple.
We're gonna talk to Zoe tomorrow when she gets in here. I'm gonna get her side of the story before we make judgment, and then we're gonna carry out
I started crying.
retribution. You really start to cry.
Yeah, it hurt so bad. I was
Sunburns
so
are
sunburned.
terrible.
And she walked up to me and smacked me. I was like, oh my god.
Sunburns are terrible. All right, go back a couple pages in the notes. I'm going to try to catch us up here with transmutation of elements. We had skipped a little bit of this. So the conversion of an atom of one element to an atom of another is called a transmutation. And there are two types of transmutations that we're going to talk about. One is called natural, one is called artificial. When you have a natural transmutation, is one way that transmutations occur, and the clue to this, when you have a natural transmutation, is that you will only have one reactant. Now, you can also have what is called artificial transmutation, and that occurs when you have a high energy particle bombard the nucleus of an atom. And we call this an artificial transmutation. Yes, it is. Yep, so they do this in these particle accelerators where they collide neutrons or other high energy particles into an atom's nucleus. Now, in artificial transmutation, you have a clue here of what it is, and the clue is you're going to have two reactants. So I will try to give you here an example of both. Okay, so real quick, what can they use for high energy particles? First of all, oftentimes they're going to be using a neutron. All right. It works well to penetrate. What's that? N. Yep. 1N0. It works well because it has no charge. Neutrons obviously are chargeless, and it can penetrate the atom well because it doesn't get repelled or attracted. So this can penetrate the nucleus of another atom very well. Okay, so the 1N0 can penetrate the nucleus of other atoms well. Sometimes they will use gamma particles or sometimes alpha particles as well. Okay, I'm going to make two columns here. We'll do natural and we'll do artificial on this side. Okay, remember, within artificial transmutation, you have one reactant. With a natural transmutation, one reactant. With an artificial transmutation, you will have two reactants. Okay? So here's what let's do natural first. Here's what a natural transmutation looks like. A very common one that takes place is the breakdown of carbon-14 by radioactive decay, and this is a beta particle emitter. So, just to give us some practice, what would be the other particle that we get? It emits a beta particle. What's that, Rowan? Yep, you know we're going to get 7, 14, and our element would be nitrogen indeed. So, carbon-14 breaks down radioactively by beta emission to produce nitrogen 14-7. That is naturally occurring. It doesn't require the bombardment of carbon-14. It will occur on its own. On the other hand, if you want to basically do a reaction with aluminum 2713, you can shoot a helium helium particle and I meant alpha particle. You can shoot an alpha particle at an aluminum atom, and when you do so, it will produce a neutron and phosphorus 3015. And here's really what I want you to recognize. Anytime you have two reactants, that is showing you that it's artificial transmutation. That is showing you that it's artificial transmutation. Okay.
How did you get 30?
For this mass, total of 27 and 41 is the 31 on the left. So you need to add something to 1 to get 31. That's where the 30 comes from. Yep. Remember the top number, which is always the atomic mass, you don't get that from the reference table because there are a numerous amount of isotopes for each atom. So you get the bottom number from the reference table. So obviously, so what can you add to 0 to get 15? You got to add 15, which is always going to be phosphorus. 15 is always phosphorus for the bottom number, but it doesn't mean that phosphorus always has a mass of 30. It could
I
be
just
different.
added the
Yep, no problem. You added wrong. Yep. Yeah. Okay, very good. I'm going to call it for the day. I just wanted to go over that this next page here we're going to cross out because we've already discussed it. And tomorrow we are going to talk about nuclear fission and nuclear fusion, dealing with nuclear reactors. Were you really? In terms of like the atomic bomb or? Okay, neat. So we'll jump into that tomorrow. Where are you looking? I gotta look it up. Yeah, my chart is a little bit different, so let me look here. Yeah, we are gonna do that. Yep, then we'll do fission, fusion. Yep. So we'll start actually there. Say that one more time, Rowan. That one has been assigned. You already did it?